and then next week, since we have test, so maybe one day I can spend on reviewing the stuff. So I thought to start with a new material today. Okay, so we started recording, right? Okay, second order linear differential equation. So this equation right here, as you can see, is linear because there is no y multiplication with y prime, or you don't even have a y square term. Function of x can be anything, sine, cosine. So this is a linear second order differential equation. Order is 2. So now the terminology associated to this differential equation is right hand side fx is called as a forcing term. So forcing term in this differential equation will be fx, and coefficients will be px and qx. Now if this px function and qx function is continuous on some interval together with fx to be continuous, then this differential equation solution will exist. So we will have a solution for this differential equation. So in order to say that solution is there, you just have to check whether px and qx are continuous on some interval. Okay, and this is also called a standard form for second order differential equation. Okay, now we will learn how we will solve these differential equations. We will also learn what are the applications in which, if we start modeling, we will end up in this kind of differential equation. So let's go slowly. So this one is yesterday, and deleting the slide from here. And this one also. Okay, now the concept of linearity remains the same as the way we were checking first order differential equation to be linear. For second order differential equation also, you will think like a mechanism happening in some box, and this mechanism is that if you input a function yx inside this machine, say, it will start computing the second derivative of y, it will add px with y prime and then qx with y, and then it will spit out the function fx. Okay, in order to check linearity, we will only be focusing on this mechanism. So we will define an operator L of y as y double prime plus pxy prime plus qx times y. Now if this operator L, which operates on functions, yx is unknown function in this differential equation, if this operator is linear, then we will call this differential equation to be linear. So if this L, which we are treating like as a function here, if this L is linear, then this differential equation will be linear. So given any differential equation, you collect all y derivative terms and y terms and define an operator, and then check whether that's linear or not. If it's third order, fourth order, fifth order, any order, you just collect everything which is left inside. Now here, in order to check linearity, let ux and vx be any two C2 functions. So ux and vx are C2 functions. The reason I considered C2, because we are taking a double derivative. So we are assuming these functions to be differentiable twice, and then, well, we don't need derivative to be continuous, but just to be on the safer side, I consider C2. So consider the sum of it, ux plus c times vx. Consider this. So by definition, it is nothing but ux plus c times vx double derivative plus px ux plus c times vx single derivative plus qx ux plus c times vx. Okay. So I am considering a linear combination of these two functions ux and vx. C here is scalar. So let's say here that C belongs to a real number R. So C is a real number and we are considering a linear combination. If this right hand side turns out to be L of this plus C times L of this, then we will call this L to be linear. So let's simplify the right hand side. So what is the right hand side? How we will simplify it? So what should I do further after this step? What can we do? Ux plus c times vx double derivative. I need to remove these brackets and simplify this expression on the right hand side. So what can I write? Anyone? How can I simplify the sum of two function double derivative? It's same idea which I told you, e to the power 3x plus e to the power 5x double derivative will be what? So ux plus c times vx double derivative is equals to e to the power 3x and e to the power 5x double derivative is what? And let me put here c to be as 4. This is say c, this is your u and this is your v. Then how will you simplify this expression? You will differentiate each of them, right? And you will pull the c out. Okay, so if you're pulling the c out and differentiating each of them, so if I do this double derivative plus c times vx double derivative plus what will happen to this one now? Same idea. You are now taking first derivative. So you will multiply ux prime and then you will multiply vx prime. That's it. And then this is already simplified here. Last term qx you multiply in ux and c is just a scalar. Qx multiply with vx. Now c is like this 4 and e to the power 5x is like this v. So c vx double prime, I can take the c out, right, from here. So I'll take the c out. And I'm just now simplifying it by multiplying and removing all these parentheses. And the last term is qx ux plus c qx vx. Now I will collect all the terms which is containing C. This term and this term, and take the C common. So all these red terms will give me what? So I collected U terms which have U, and I'm basically, to be honest with you, I'm collecting V terms here, all the V terms. So collecting all U terms, this whole thing is nothing but what? I think you should be able to see right now what we are finally ending up into. So this thing, this U terms together will give us, what is this by definition? This whole thing is equals to just this much. This is equals to right. So L of yx is defined to be as this, and if in place of y I have u, so then this is equals to, the compact form of this will be L of ux. Very good. L of ux. Constant is taken out, and then we get L of vx. Same way. So L of sum is equals to L of each individual, and then we are adding. So this means this L is linear. So this is basically how you will check linearity. You take a linear combination, and if linear combination gets split up into each separately, then we call this L to be linear. Okay, now can anybody give me an example of L? So L is like a function here, which input is function and it's giving out, this is a result of L, and this L is linear. Can you give me any other L which will also follow this property? Say it again.
An actual function of
e to the x. Will e to the x will follow this property? So how will you check? I mean, you are inputting a function in that. So example should be something you input and it spits out some function. So function is getting input and it's spitting out function. And e to the x, x is input and you are getting e to the x, right? That's how you're thinking. But you think now in terms of you're inputting a function and then it's spitting out a function. So what could be the example? Here I am inputting yx function and it is spitting out derivatives, and it's the resultant will be a function. So give me an example of L where input is a function and output is also a function, and it will be linear, and it will be satisfying this property. So this is second order linear differential equation. Now you may say, okay, if I just take y double prime, L of y is equals to y double prime. Is it linear? L of y equals to y, linear. L of y equals to y prime, linear. So any derivative will be linear. Now think beyond derivatives. Anything else? all derivatives are linear if you don't multiply with the y in it. So basically you gave me a bunch of examples here, infinitely many in some sense. L of y equals to y prime is linear, L of y equals to y double prime is linear, L of y equals to y triple prime is linear, and so on. Now forget about derivative, you are inputting a function and you are doing something else. So what could be another type of example? Inputting a function and then not taking a derivative, not just saying y, identity function, but something else. Where you can do this kind of idea, you can split it. So with derivative you can split it, right? Is there anything else where you can do the same thing, splitting?
So would it be like the natural log of A over B? So you can split that, right?
Natural log of A over B. So if you are inputting, you will be inputting what function then? Maybe your output is natural log of A over B, but what would be the input function? Tricky, right? So you have to do something with the function. If you are inserting a function and doing something with the function, and the way you are doing it such that it will be splitting out like this. If I say this, I'm inputting a function. You may say, well, you are now not spitting out the function, you are spitting out a value here, because after taking a limit it will be some value, and limit of all the function is also not defined. So we are only considering those functions whose limit is defined. So if our domain contains all those functions whose limit is defined as x approaches to infinity, then if I take this as an example, is it linear? If my domain contain all the function whose limit as x approaches to infinity exist, then is this L a linear operator or linear function? What do you say? Because you will take function ux plus c times vx, and then c can be taken out, and the limit of sum is sum of limits. So that's why this is linear. If domain contains all those functions whose limit exists, as x approaches to infinity, then this makes sense. This will be linear. Any other example? But idea should be that the same thing. Sum of that is equals to, you can distribute it. Here sum of derivative of sum is sum of derivatives. And the same idea applied with the limit here. Now think about something else. I want to do something with this function y, and it should be linear. If I tell you, you'll say, aha, you know this example. So I'm just still waiting. Forget about derivative. Is there something which is similar to derivative?
Integration.
Integral. If I have a function and I integrate that function, and if I add u plus c times vx and I integrate it, u integral plus c will take out, we can take out an integral of v. Right? So this is also linear. So integrals are also linear. Now why we keep emphasizing on linearity? The reason we keep emphasizing on linearity is long back when engineers were working on some problems, they they thought, okay, there is some structure here coming out and we want to see the results. But the theorems which Fourier designed long back, and nobody could figure out what is the connection of those theorems, abstract theorem, with what engineers are doing. It's like there's no connection. But if we give an abstract idea to differential equation, which is linearity, then suppose in future you come across something, we want this kind of characteristic. You go back in the literature, look for a abstract result and see there is a connection. That time you will see there is a bunch of properties of linear operator. Linear operators are very useful. They have a lot of properties. And then you might use that property to justify a physical situation. So the reason we define abstract concept is because, think like this, if you are just specific example you are working on, you would not able to see the real depth of the class of differential equation. But if you understand this class of differential equations are linear, then you go back and understand what are the properties of linear operators. Now in the properties of linear operator you figure out something and you say, oh, can my differential equation will also have this? Yes, it will have that. So this is the reason why we learn abstract concept. It's not like I'm some crazy mathematician trying to just want you to keep reading about this abstract idea. There is a lot significance. And if you really want to do eventually application, a real research in application, then you have to go back and forth. Okay, let's go ahead then. Coming to this, we will, in order to solve any difficult problem, this is a key. We should always break a problem into simpler problems. Because any big problem is a result of simple problems. So if you are good at breaking a difficult problem into small, simpler problems, you can able to handle research in future. Because this is the most important part. So if I have this big gigantic differential equation I want to solve, and suppose somebody gives me px, qx and fx, my first goal is to break this problem. And breaking is, maybe I'll say, okay, can I solve this? Maybe I cannot solve the entire problem, but can I solve this? Equals to 0. And say I was able to solve this, then I'll move forward and say, okay, now let me take some function x, not very difficult function, but x function, and see if I can solve this. And like this, march forward. Okay, so this is called homogeneous. Now, notion of homogeneity in second order is very much different from the first order. In first order, what we were doing to check homogeneity? We were taking f of kx, ky, right? You remember? And then we were trying to simplify it. Here, if right hand side, if forcing term is 0, then we will call that differential equation homogeneous. If forcing term is non-zero, then y double prime plus pxy prime plus qxy is non-homogeneous. And now onwards I will be using this shorthand NH for non-homogeneous and H for homogeneous. Okay, so we will focus first understanding how we will solve homogeneous, and then we will move on to non-homogeneous problems. So homogeneous problem also, now if you can see this differential equation, if px and qx are some function of x, it is hard to solve. And you start thinking what are the methods. So you go with simpler approach. Maybe let's first understand what happens if px and qx are constants. Can we solve that problem, which is simpler? Yes, we can. And that's the easiest of all the problems. Okay, so we will be focusing eventually on that idea when px and qx are constant. But before this, we will address this question. Given fx non-zero, what is the associated homogeneous differential equation to 1? So suppose somebody comes and they give you fx to be non-zero. What is the associated homogeneous equation to this equation? you will just replace fx with 0. So this is associated homogeneous problem for a non-homogeneous. Okay. Second order differential equation will also give you unique solution if you specify initial condition. So if I have this problem, non-homogeneous only, but how many initial condition do I need in order to get a unique solution? For second order differential equation, how many initial condition do we need? 2. So y at A to be B and y prime at the same position A to be some C. Now this we will call as IVP for second order differential equation. We need 2 initial condition. Okay, and it will have a unique solution. Now we not just need the function initially what it is, but we need the derivative as well. Okay, so let's move then. This is key in solving second order linear differential equation. If you are able to find a solution of associated homogeneous differential equation, then you will be able to solve non-homogeneous problem also, because there is a connection. So given a non-homogeneous problem, every time you have to find a solution of associated homogeneous problem. So this is what it is saying. Why are we concerned about associated homogeneous differential equation? They turn out to be very useful in finding solution of non-homogeneous problem, and we will see. You will see how. Okay, so let's start solving them. P and Q, I am assuming now I have considered a simpler problem. They are constants. And the next case will be when they are functions of x. In order to solve this differential equation, from your first written homework, you remember that if I gave you this function where p and q are constants, say 3y prime plus 5y equals to 0, what else was there in the problem in written homework 1? You have seen this kind of differential equation in written homework 1. What were you doing with those differential equations? You were plugging e to the power lambda x, right? And then you're trying to check the lambda. So I'm doing the same thing here, e to the power lambda x double prime plus 3 times e to the power lambda x prime plus 5 times e to the power lambda x is equals to 0. So I can take now e to the power lambda x out, and I am left with lambda square plus 3 lambda plus 5 equals to 0. Since e to the power lambda x is non-zero, this has to be 0. There is a name for this equation. It is called as characteristic equation. Characteristic equation. What is the reason why we can apply this idea in these type of differential equation? And if not, even like if it is third order, we can still apply this. But what is the speciality about this, that this thing works here and we get a polynomial?
What is this? Because every time you take the derivative of it, the function doesn't change. Really. You get the constant that pops out, But you still keep that.
You still keep that.
That e to the x.
So what is making that possible?
Oh, just that
The way differential equation is?
well, no, just the way that e to the x happens to be number.
Because it's constant coefficient. Because it's a constant coefficient, e to the power lambda x is not accompanied by any x function here. And if there was 3x here, then you will end up here 3x lambda, and then now you can't do anything. You can't get lambda. So if it's a constant coefficient, you can always apply this trick, and this will call characteristic equation. You find the roots of it. Once you have roots, then so for example in this, what are the roots? You have complex roots. We will see how to deal with complex roots. But for the real roots, suppose if I had here equation which had real roots, then those values of lambda, if you consider here, you get two functions which satisfy this differential equation, right? Two functions which satisfy this differential equation. And if you consider a linear combination of them, you get a general solution for this problem. Okay? So that's the way we will be approaching. Okay, but before this, what is a characteristic polynomial? Characteristic polynomial for this specific equation is 3 lambda plus 5. We will then focus on fundamental set and then Wronskian. Okay, so once we have these tools ready, then we will start building a solution for the differential equation. So we are just gathering tools here now. Okay, so this we got it. What is the characteristic polynomial associated to this one if p and q are constant? What is the idea? You replace, if you don't want to keep plugging e to the power lambda x every time and differentiating it, the straightforward trick is replace y with 1, y prime with lambda, y double prime with lambda square. So you are treating this as a zeroth derivative. So you get here lambda to the power 0, which is 1. So you replace by 1 lambda lambda square, and if it's y triple prime, you replace by lambda cube, and so on. And you get a polynomial, you solve for that polynomial, all the roots, you start getting a function, e to the power that will be satisfying this differential equation. Okay, so polynomial is here lambda square plus p lambda plus q. It's very usual mistake students do that they replace y with lambda. Don't replace y with lambda. Your polynomial will be wrong. So y with 1, and this is characteristic polynomial. Okay. If I put here e equals to 0, will it still be a polynomial? Because some fundamentals of like which, even though you know what is polynomial, but sometimes you say, okay, this equals to 0. That would be characteristic equation. If you're writing polynomial, you just leave it like this. If you're writing equation, you write equals to 0. So just different terminology. Okay. Wronskian. What is Wronskian? Very important for second order differential equation. Wronskian of 2 function, I will get to more depth of it. First I'll just define it. Wronskian of 2 function is determinant of fx gx f prime x g prime x. This is equals to fx g prime x minus gx f prime x. So if somebody gives me 2 input function, then I will take determinant, put them in a row and differentiate and then find this. So what does it look like? It looks like a product rule but with the plus replaced by minus here. But we will see one more feature here. If I try to find a Wronskian of cosine and sine, I will get here cosine x sine x minus sine x cosine x, and then it will be cosine square x plus sine square x, which is 1. Now for me, you compute Wronskian of sine and cosine x. Everyone, compute the Wronskian of sine x and cosine x. Same, use the definition here of Wronskian and compute the Wronskian of sine and cosine. And tell me the difference you note in both of them. Done? Here is the definition. You place the function sine here, cosine here, take the derivative of cosine, take the derivative of sine, find the determinant. What you will get? Negative. Everybody is getting negative 1. So what do you notice then? So what's the difference then from this and this? What could be the conjecture out of it? If we reverse the order, we flip the sign. So next time onwards, you don't have to compute it. Next time onwards, you just remember this thing, that Wronskian of fx and gx is equals to negative of Wronskian of gx and fx. Okay, so this is how you will do. Now let's find the Wronskian of this. By definition, it is determinant of e to the x, e to the pi minus x, e to the x minus e to the minus x. So this will turn out to be negative e to the x, e to the minus x minus e to the minus x, e to the x. What is this equals to?
Or
just negative 2. So negative 2. You noticed here that if e to the power lambda x and e to the power minus lambda x you consider here, then you will still get negative 2 as a Wronskian. So whenever Wronskian is non-zero, that will imply functions are linearly independent. Now what do we mean by functions to be linearly independent? So we have to formulate it mathematically. Okay, so fx and gx are said to be linearly dependent if there exists a non-zero scalar c such that fx is equals to constant times dx. So function f and g will be said to be linearly dependent if you can find a constant c such that fx is a scalar multiple of that function. Then they are called linearly dependent. And if this does not happen, they will be called as linearly independent. Now then question comes, how do we check this mathematically? Like, this is a definition. We always from a definition try to go to a formula by which we can test it or check it. So here are some of the results which I have collected. Given a differential equation, this is second order, and these will hold even if coefficients are not constant. Coefficient can be constant or function of x, these results will hold. Consider the second order linear differential equation. If Wronskian is non-zero, then the functions are linearly independent. And you need it on for some value of x in the interval you are looking for a solution. So if you compute a Wronskian of f1 and f2, and if Wronskian turns out to be non-zero, functions are linearly independent. Okay, so that's a test. And it's a both the way true, if and only if. If Wronskian is 0, what will that imply? Right, you might think they are dependent, but they will be dependent only if they are satisfying some second order differential equation. But if they are not a solution of second order differential equation, you cannot say anything about those functions. Okay, so other way around is only true if functions are solution of second order differential equation. So remember this point, it's very important. Okay, so I'll write it down here. Wronskian of fx and gx equals to 0 does not imply fx and gx are linearly dependent. But if fx and gx satisfies same differential equation, and Wronskian of those two functions is 0, that will imply fx and gx are linearly dependent. And this is 0 not for 1, for all x in that interval which you are looking for a solution. This should be 0 for every so even if this is 0 for every point in the interval, that will not imply LD. But if you figured out that those two functions are satisfying some same differential equation and this is 0, then you can say yes, they are LD. Okay, so this is the key here. Why are we interested in linearly independent solution? The reason we are interested in linearly independent solution is because they will form fundamental set. So I will leave these theorems for you to read, but in between I will insert now slide, and we will start defining fundamental set. Okay, so what is fundamental set? We have learned Wronskian. What is the significance of Wronskian? Wronskian can help us to understand whether functions are Li or not. So what is a fundamental set? Set of solutions of y double prime plus pxy prime plus qxy is equals to 0. So this is a question. Answer is, there will be two members in this set because the order of differential equation is 2. So this is said to be fundamental set, and I would say A because there can be many fundamental sets of solution of star if and only if when do we call this set, which is in curly braces, we have two functions, to be fundamental if and only if Wronskian of these two functions should be non-zero. For some x in the interval we are looking for solution, and y1 and y2 should satisfy differential equation. Should satisfy DE y double prime plus pxy prime plus qxy equals to 0. So if we can able to find two functions which satisfy differential equation and whose Wronskian is non-zero, then we will call those functions together in set form as fundamental set. So in the problems you were working in homework 1, when you were finding lambda 2 values, if you place those lambda value over E and collect those two functions and find their Wronskian, if Wronskian is non-zero, you can say those two functions are fundamental set, forming a fundamental set for this specific differential equation. Now there is a, notice a word here, fundamental set of solutions. So these two should be a solution of differential equation also, right? So e to the power that is a solution, and e to the power another value is also a solution. So therefore that's how. And if in exam I ask you to find fundamental set, you will be giving in this notation curly braces and putting the functions. If you give me two functions by separating by comma, I will not give you any point for that. Set means in set form. That's the reason I wrote it down as curly braces and then wrote down two functions here. Okay. So this is a fundamental set. Now let's do examples on fundamental set. Example 1. Given the differential equation y double prime minus 5y prime plus 6y is equals to 0, show that e to the power 2x and e to the power 3x forms the fundamental set of solutions of y double prime minus 5y prime plus 6y is equals to 0. Okay. So we want to verify that these two members together will form the fundamental set of solution of this differential equation. So how we will proceed? We want to show first, step 1, what is the Wronskian of e to the power 2x and e to the power 3x. Determinant of e to the 2x, e to the 3x, 2e to the 2x, 3e to the 3x, and this will be equals to 3 minus 2, which is 1, e to the power 5x. Right? E to the 2x times 3e to the 3x will be 3 to the power 5x minus 2e to the power 5x. Right? You all are with me? Okay. Is it 0? No. So one part is satisfied. This is non-zero. Step 2. So are they satisfying the differential equation? Let's check. If I plug e to the power 2x in this, what will I get? Double derivative is 4 e to the 2x, single is 10, 2 times 5 10, and then plus 6 e to the 2x, so that's 0. So yes, it is satisfying. What about e to the 3x? E to the 3x double derivative minus 5 e to the 3x single derivative plus 6 e to the 3x, so it is 9 e to the 3x minus 15 e to the 3x plus 6 e to the 3x, so it is also 0. So yes, so they both are solution of this differential equation. Wronskian of them is non-zero, so that means they will form fundamental set, and we have shown that they will form fundamental set. Now what is the natural question to ask at this moment? So given two function, you can check whether they are forming a fundamental set or not, like this. So then what you will ask? It's very important to know what to ask, because if you don't know what to ask, you're not proceeding further at all. And if you know what to ask, you will develop the flow of questions in that manner that if somebody start answering those questions, whole D is finished. You finish the differential equation. You learn the differential equation. So a goal should be, after every concept, what is a legitimate question at this moment? Or if not even legitimate, what could be the question? And then other questions also come side by side. Why we are doing this? So I gave two functions and we verified they are forming fundamental set. Now it's very natural for you to ask what?
Maybe only two?
You only need two because it's a second order differential equation. If you get two, then because solution is a two parameter family, so once you have two functions, linear combination of them will be your general solution. But here you were given the function and you were checking. You might say, how we will find those functions which will form fundamental set, right? Here I gave you e to the power 2x and e to the power 3x. Given a differential equation, how will you find those two functions? And is this concept only to constant coefficient, or is this concept works with non-constant coefficient also? Fundamental set concept. It works for non-constant also. If you're able to find two functions which satisfy that differential equation and Wronskian and non-zero, then they will form fundamental set. And this concept is in context of what kind of differential equation? Homogeneous. So fundamental set idea is we are only focusing right now on homogeneous. So we are trying to understand what are all the solution of this homogeneous. And once we have all the solution of homogeneous, then we will go ahead and try to figure out what are the solution of non-homogeneous, because that will help us, the class of solution of homogeneous, to figure that out. Okay, so this is there. Now, having this, I can say, so e to the power 2x and e to the 3x forms a fundamental set. Of y double prime, fundamental set of solution of this. So that means general solution will be c1 e to the 2x plus c2 e to the 3x. So all these will satisfy the differential equation. Now, why did somebody pick the terminology fundamental set? Is there a reason behind saying it as a fundamental set of solutions? And why from fundamental, if we take a linear combination, we get everything? So if you understand this thing, this answer of this question, then you got this concept completely. So, how many of you have taken linear algebra before? 1, 2, 3, 4. Linear algebra? Have you taken linear algebra?
Yeah.
Which one? 343, 242?
242.
242? Okay. No linear algebra? Not? No. Okay, so 242 will also be will be enough. So if you think like this, you would, those who have taken 242 and even 343, you remember the word basis in linear algebra? What is the connection of basis with the vector space? If you have a basis, so for R2, what is a basis? Basis of R2. Can you give me the basis of R2? Just one basis. There are so many bases possible, but just one basis of R2. Is this a basis? Right? So basis means a linearly independent set which spans whole R2. And when this word linear independence come, what you do, you take a linear combination and you find those scalars. And if those scalars are 0, the members are Li. And for span, it means if I want to write 2, 3 in R2, how can I write 2, 3 in terms of these two in R2? 2, 3 is a point in R2. And I want to write it down in terms of these 2 points. Can I do this? Right? Those who have taken or those who have not taken, can I do this to get 2, 3? Right? Looks very intuitive, correct? And any point, it's not just 2 comma 3, any point 5 comma 4 I can do like this. So that means if I get a basis or if I get a fundamental set of solution, I will take a linear combination and I will generate every single function which will satisfy my differential equation. So if you're able to get a basis of R2, you can give any point of R2, x comma y will be nothing but x times 1 0 plus y times 0 1. You can give any point of R2 using these 2 points. So using those 2 functions, e to the power 2x and e to the power 3x, you can give any solution of the differential equation if you multiply by constants. Like this, if you multiply by constant. And if you want a unique solution with initial condition, your C1, C2 will be uniquely determined. So if you have to find just 2 comma 3, how you can express like this? 2 is the possibility, 3 is the possibility. Is there any other possibility? Is there any other way I can express 2 comma 3 in terms of these 2? No, I cannot. So that means this is unique representation. And that's a connection with the differential equation, you get a unique solution. Okay? So your linear algebra is extremely tied up with your theory of differential equation. Fundamental set is nothing but basis for the family of solutions. And vector space now is not R2, it's entire family of solution of that differential equation, and basis is fundamental set which you are trying to find in this example. So you found out e to the power 3x and e to the power 2x is a basis, and if you take linear combination of it, you get every solution of this differential equation like this. This is the reason why I will keep writing C1, C2, C3 and so on depending on the order of differential equation, and I keep adding them. Because on the back of my mind, linear algebra is going that this is a basis and everything will be linear combination of that. So, okay, so having this now, you all got this clear. Now let's try to understand how to find fundamental set, how to find basis in differential equation. Given any differential equation, how will you find basis or a fundamental set? Once you have that, you have solution. How do we find fundamental set? Okay, step 1, write down the characteristic equation. And you can write it down by replacing y double prime with lambda square, which I just now told you. So you will, step 1, you will write down characteristic polynomial. For this particular equation, y double prime plus py prime plus qy, polynomial is lambda square plus p lambda plus q. This is Cp. My shorthand for characteristic polynomial will be Cp. So this is Cp. Okay. Now step 2, solve this characteristic equation. Now this is equation. So you will solve this. Now note one thing, that if you have a constant coefficient, you can write down a polynomial. But if you do not have constant coefficient, we will learn next time how we will proceed for fundamental set. So this is for constant coefficient. We are addressing this question for constant coefficient dE only. Okay, what are the possibilities of roots for this polynomial? Second degree equation, what are the possibilities of roots? Both real and distinct. Both real and equal. What next? Complex. Okay, so if lambda 1 and lambda 2 are distinct roots, and here I should not put equal here, and here lambda 1 is equals to lambda 2, and here lambda 1 is a plus ib, and another has to be its conjugate, a minus ib. So if this is there, what is my fundamental set in each situation? So fundamental set will be e to the power lambda 1x, e to the power lambda 2x. Fundamental set in this situation will be e to the power lambda 1x x times e to the power lambda 1x. You multiply by x, and I will address this question why multiplying by x. But right now I am just writing down the fundamental set. And fundamental set, when you have a complex root, e to the power ax cosine bx, e to the power ax sine bx. Okay. So if roots are both real and distinct, this will be the fundamental set, and linear combination of this will give us then entire family of solution, because it's a basis. If roots are equal, you multiply by x and then take a linear combination. If roots are complex, you take linear combination of these two functions and you get a general solution. So this case you have already done in written homework 1, when you were plugging e to the power lambda and you are getting lambda values, two different values. So this you have already done. This one, suppose polynomial is like that, you get two repeated roots, then in that case you multiply by x. There is a method by which we can derive it also, why the second one comes like this. We will do it next time. And here if you have imaginary part, you will consider this. Now why for the imaginary I didn't consider e to the power a plus ib times x, like the way I considered here, right? That's another question you can ask, that here your roots were lambda 1, lambda 2, and you just took a power of that and you got a fundamental set. But in complex, you never took a power of that, you just wrote down two function. Why instead of writing that, I was not writing e to the power a plus ibx? Why? This is a question you should ask me. Actually, I am asking you the questions. But I remember those days when I don't even let professor to move in the class further without getting any answers to every single step they are writing on the board. So the moment I did that, you should say, wait. You wrote down there e to the power lambda 1, lambda 2. You wrote down there, that's you are saying you can clarify later on. But why now this one you just wrote it down like this? Why you didn't wrote down like e to the power a plus ibx?
Is it because there's a positive and negative component to cosine and sine, if you do that cross product, is the difference between a 1 and a negative 1? Is that right?
Well, first you are kind of getting in the loop of the idea, but first of all, I don't want complex functions to be my solution. I'm in a real world. For a differential equation, I want solution to be real. The moment I introduce I, it's not making sense because we are looking for a real solution. But if I further simplify this expression and try to see what is happening, I will get e to the power ax and I will get e to the power ibx by rule of exponents, right? Now what is e to the power ibx? It is a famous identity which is called as Euler's identity. E to the power ibx is Euler's, you will find everywhere. He will not leave you because every single thing which came initially, most of the thing, I should not say every single thing, most of it was work done by him in context of differential equation. So using the Euler's identity, we get cosine bx plus I sine bx. Now the same idea with e to the power a minus I bx. So cosine, now this time you have a negative sign instead of positive sign. And you end up getting two functions, but difficulty is that they have this I appearing and you cannot take this to be a solution of differential equation because you want real solution. Then how we will move further after this idea by seeing them? Well, this is also a very important property. Now again I am getting back to linearity in some sense. If I have this differential equation, and if one function satisfies this differential equation, another function is satisfying that differential equation, and I'm not concerned about these functions at all because they are complex, but I do want to get a real out of it. Is y1 plus y2 satisfy this differential equation, or will this satisfy the differential equation? The big question mark here. y1 satisfy differential equation, y2 satisfy differential equation. Will y1 plus y2 satisfy differential equation? Because y1 is say complex, I am not interested, but it is satisfying. y2 is a complex, I am not interested, but it is satisfying. But y1 plus y2, as you can see, sine I sine bx term will go away, and we will get e to the power x cosine bx. If this is true, y1 plus y2 will solve, then I can get a real part out of that. And I am looking for only one solution of dE. And same way, I will find another solution of dE. And once these two solutions I have got, then I will take a Wronskian, and if they are non-zero, I am good to go with the fundamental set. I just need to. I never said fundamental set is unique. As basis is not unique, fundamental set is also not unique. You just need to cook two functions which will satisfy and whose Wronskian is non-zero. This idea of y1 plus y2 is coming from linearity because this is linear differential equation. If I take a derivative and split this and apply this and this 0, I will get this as 0. So yes, sum of two solution of homogeneous dE is a solution of that homogeneous dE. And that is the reason we considered separately cosine and sine. because each of them is a solution and sum of them is also a solution. And that's how we got e to the power ax cosine bx is a solution. Each of them is a solution and difference of them is also a solution. Scalar multiple of them is also a solution. So I will take a difference, divide by I because it's a scalar, and I get scalar in context of complex, and I'll get the again e to the power ax sine bx. So these two functions we got from idea of linearity of second order differential equation, and therefore we are focusing only on real solutions, not complex solutions, because complex will not give us a solution of that differential equation in the real. It will not make sense. So this is the reason behind why people always write e to the power cosine bx and this rather than writing fully the root and multiplying by x, because they are looking for real solution, first thing. Second, linear combination, addition is a solution and difference is a solution, and scalar multiplication is a solution. Okay, so that being said, another important property associated with complex root is solution has rotation. Solution will not be like a function going, exponential is like a function going. Linear combination will be a curve of exponential, mimicking exponential function. But here you can see there will be a rotation in a solution. Solution curve will give you a rotation behavior. So whenever roots are complex, that very moment it should come in your mind, solution will be having a spiraling behavior. Complex root give rise to spiraling behavior in the solution. Okay, so that's it for today. We will start working out problems on Monday.